So we're going to discuss this time lecture 2. Good afternoon everyone. Lecture 2 is about double integrals in Cartesian coordinates. We already finished the topic on line integrals. That's the first topic for the finals. We are now on double integrals in Cartesian coordinates. Later on, we'll be discussing um, this topic, double integrals in polar coordinates and applications, since center of mass and moments of inertia is an optional topic. Then we will discuss triple integrals in Cartesian coordinates and applications, as well as cylindrical and spherical coordinates. Triple integrals in cylindrical coordinates and applications will all be discussed, to be followed by your triple integrals in spherical coordinates and applications. Our intended learning outcome is for you to learn multiple integrals and some of their applications. So in the single integral, if you remember, you have a real valued function f, which is bounded on AB. And if we take the partition delta of AB, then the integral from a to b of f of x dx is defined to be the limit of the summation of f of psi sub I delta sub I x as delta approaches 0, I equal to 1 to n. So I mean to say, this is geometrically the area under the given curve f of x from a to b. Now, f is a bounded real function defined on this closed region R in R squared. A partition delta of R is formed by drawing lines parallel to the coordinate axis and obtain a network of rectangular subregions that cover R. The norm of delta, denoted by this, is determined by the length of the longest diagonal of a rectangular subregion of the partition. So when we talk about partition delta this time, we have parallel lines, okay, parallel lines, which are parallel to the coordinate axis, and you have there the norm delta, this one, length of the longest diagonal. So here, if we take this one sub interval, this becomes this one, this one sub interval. And what do we have here? We take a look at this one. We have this one. This is delta sub I y here and delta sub I x. Okay, so what do we have here? Delta sub I y and delta sub I x. From here, f of psi sub I, gamma sub I, p sub 2. So this is the function z equals f of xy. And this one subinterval, for that we have delta sub I x and delta sub I y here. And this is your z equals f at x sub y from here to here. So this is your f at psi sub I, what gamma sub I, at 1. The interval from one rectangular coordinate is A2 to A1, and the other one is from B1 here, B sub 1 to B sub 2. This is this portion, this one. Now, If we let delta sub I A be the area of the rectangular subregion with the length delta sub I x and the width delta sub I y, that means to say that delta sub I A is equal to the product of delta sub I x times delta sub I y. And we can take psi sub I, gamma sub I on the ith rectangular subregion and form the product. This one, f of psi sub I, gamma sub I times delta sub I x times delta sub. Because this one is the height, and this is the width, and this is the length. If we take such n rectangular subregions, take its summation, then we actually take the entire thing. This one, this one small thing here is basically just this one part. So if we take the summation of all of this one part here, then we take all of the subregions here, subintervals, and come up with the interval from A to B, or from C to D. So entire thing. Remember that this is just A sub 1, B sub 1, meaning to say those are these small subintervals there. So that if we take the limit of this sum, as the norm approaches zero, meaning to say we make delta as small as possible, we make many small subintervals. Then, and we take its summation, is f of psi sub I, gamma sub I, delta sub I a, wherein your delta sub I a is this, delta sub I x, delta sub I y. You take the summation of that one, delta sub I a is your area there, and you let delta approach zero, then you approximate actually the value for the entire thing, this one. It's, meaning to say, we come up with a formal definition of your double integral, that is, you have a function of the variables x, y, defined in a closed rectangular region R, and the number L is said to be the double integral of f over R. If for any epsilon greater than 0, there exists a delta greater than 0, such that for every partition delta, for which delta is less than 0, and for all possible selections of this point in the ith rectangle, we come up with a value summation of f of psi sub I, gamma sub I, delta sub I, a minus your L, which is supposed to be the limit less than epsilon I equal to 1 to n. And that forms the definition for the double integral of f over R, which is, if you let f be a function of the variables x and y defined in the closed region R, contained in R squared, the double integral f over R by this one function of x sub y, f of xy dA is equal to the limit of the summation of f of psi sub I, gamma sub I, delta sub I, a, delta approaches 0, I equal to 1 up to n, provided the limit exists and the same for every choice of points psi sub I, gamma sub I in R sub I for each I equal to 1 up to n. So that's the definition of your double integral. It's actually the limit of the summation of f of psi sub I, gamma sub I, delta sub I, a, delta approaches here. Meaning to say, we make those sub-intervals as small as possible. It is approaching 0, but it's not equal to 0. You have theorem 2.4, which says that if you let AB be the closed interval, we have phi sub 1 and phi sub 2 be continuous functions on AB, such that phi sub 1 of x is less than or equal to phi sub 2 of x for all x element of AB, and if R is the closed region given by this, that is, R is the region xy such that x is between A and B, and phi sub 1, to say this is a function of x, and a function phi sub 2 of x is greater than or equal to y, but it is supposed to be your phi sub 1 is less than or equal to y. then you can rewrite the double integral of this function dA, function xy at dA, to be the integral from a to b. So you have a constant value here for dx, and you have phi sub 1 to phi sub 2. You have a function for dy there for y, of f of xy. Then 2.5 says that if in this case the function is in terms of x, in terms of y, sorry, in terms of y, then you should have the inner integral to be this one in terms of y. So yeah, so you should have your dx first, integrated with respect to x, and then your function, since the constant is in terms of y, then this one, your y should be from c to d. So in this case, x here is a function in terms of y. So you have dx here. Um, if you let k be a constant real number, then if it's k times a function of xy, just like in single integral, you simply have to take out the constant and then evaluate the function dA, double integral. Similarly, you can actually have the following double integral evaluated as, if you have a sum, then you can take the double integral of a sum of dA as, take the double integral of the first function f of xy at dA plus take again, so you can distribute the double integral sign a function of cube xy dA. Theorem 2.8 says that if you have two regions, as long as the regions are um, supposed to be, you don't have intersection, okay, R1 union R2 is equal to R, so they are disjoint, and R1 and R2 are supposed to be closed regions. Then as long as f is both integrable on R1 and R2, the function is integral on both R1 and R2, then you can take the double integral as, you can take the first region, evaluate it with that function dA, plus take again the second region, evaluate it such function, as long as the regions are disjoint and they are closed regions. Theorem 2.9 says that if you have a function of xy is less than or equal to the function of g of xy, when you take the double integral of the function of xy dA over r, and you take the function of g of xy dA over r, since f of xy is less than to g of xy, then this will come up to be the double integral with respect of the function xy dA is less than or equal to double integral of the function g of xy dA. Let's take the first example. Evaluate the following iterated integral. Take a look that both the limits of integration are constant. So that means to say, if you have this function, you can rewrite it, or you can also solve it as the double integral of xy dy 2y plus 1 dx instead of dy. You come up with dx first. And since the dx here is from 0 to 1, so you can also have 0 to 1 for dx. And then dy here is from 0 to 1, so your dy can also be integral from 0 to 1. So as an exercise, you are to solve the following. Evaluate the following iterated integral, and you should come up with the same answer as this. So let's solve for example 2.10 first. Here we have this. Notice that we have to evaluate this with respect to y, and to say your x there is constant. So it would be easier to distribute this one first. So you will have xy times 2y will give you 2xy squared, and it will give us xy. So we integrate with respect to y, We'll come up with the following. So this is first your, when you distribute, you have 2xy squared plus xy dy dx. And integrating this with respect to y, this should give us 2xy cubed over 3 plus xy squared over 2. Okay? And then evaluated from 0 to 1, the x integrated from 0 to 1. Okay? So this is how it should look like. So evaluated from 0 to 1. So 2x y squared, then because it's respect to y, you have y cubed over 3. And then this is x y squared over 2 because it's with respect to y. And then from 0 to 1, so meaning to say, you replace, this is in y, so you replace your y with 1. So you will have 1 cube, so 2/3 x, which 1, so you still have 2/3 x. And this is 1 pa rin, so 1/2 x. Then because that's minus 0, so it does not change anything anymore. So you should just have the following: 2/3 x plus 1/2 x dx. Again, this is to be integrated with respect to x. So you have 2/3 x squared over 2, and you have 1/2 x squared over 2. So that should give us, evaluated from 0 to 1, should that give us this one. I'll give you time to solve and solve for the value of this integral evaluated from 0 to 1. See? Anyone? So you should have the following answer: 7 over 12. Okay? Now let's take a look at the exercise. You can do that one later on so that you can continue with our lecture. But you should come up with the same answer as this: 7 over 12. So please work on that. Now, activity 2.11, which is your next meeting, would be this: the integral from 0 to 1, 0 to 1, x minus y dx dy. You are to evaluate the following iterated integral. The answer is 1 over 3. So, what I need is the solution of this one. Example 2.12. You are to evaluate the double integral cosine of x plus y dA, where R is the region bounded by the lines y equals x, excuse me, and x equal to pi and the x-axis. So y equals x is a line that slants upward to the right. X equal to pi is, if this is your x-axis, approximately 3.14, and your x-axis, it looks like a triangular region bounded by these lines. Now, again, this is the problem. Let's take a look at the solution. The region is shown in this. It's just as what I had mentioned earlier. You have your y equal to x equal to pi, that's 3.14 approximately, and this is your x-axis. So you come up with pi, comma pi there, and you have there y equal to x. Solution: this is the double integral cosine. We are to find out what should we place in here. Since we have here dy dx, if you take a look at this region, notice that your y moves from what value? from 0, yan, y is from 0 to x. And your x moves from 0 to x, that's your y. Your x moves from 0 to pi, which is actually a constant. So meaning to say, if you just take a look at this, we have to make use of, we know that we should have the inner limits of integration for the inner integral should be the function, and the limits of integration for the outer integral should be constant. So we have to make use of ty first. You take a look at this here. Y moves from 0 to, this is not constant, it's changing, correct? 0 to y equals x. So you have dx. So cosine of x plus y dy dx. 0 to x, the cosine of x plus y dy. And when you try to solve this one first, remember that the integral of cosine is supposed to be sine. Sine. So you have sine x plus y dy, dy with respect to y. So you should have simply dy. Correct? So you already have that one. So from 0 to x. Rewriting this should give us sine of x plus x. So it will give us sine 2x minus, okay, sine of x plus, remember we have to change your y. So x plus 0. So we should have there this one. Sine of 2x minus sine of x plus 0. So you have sine of x only. And when you try to integrate this again, respect to x this time, the integral of sine is negative cosine. You have sine negative cosine. So you need actually a 2 dx. So you have to introduce 1 half. So you have negative cosine of 2x plus, okay, the integral of sine is negative cosine. So because that's a negative, that becomes plus cosine of x. So evaluated from 0 to pi. That should give us negative 1 half. What's cosine of 2 times pi? That's cosine of minus 1 half cosine of 2 pi should give us, it's cosine of 2 pi. So pi, 2 pi is there, 0. So minus 1 half cosine of 2 pi. Let me see, cosine of 2 pi. This is 1. This is 1 pi. Cosine of 2 pi is cosine of x 1. Sorry, cosine of 2 pi is 1. So negative times 1. So minus 1 half cosine of 1. Then cosine of pi. Cosine of pi is here. You have your pi here. So now minus 1. Minus, okay, but this is a plus, minus cosine of 2 pi. Again, so you have 1 half times cosine of 2 pi there. Again, 1. So minus or minus of plus 1 half is 1. Because it's 1. And then cosine of 0. What's cosine of 0? It's 1. But because you have there minus, so you have minus 1. So when you solve for that, that should give you negative 2. Okay? Now for activity 2.13, you are to evaluate this one. Double integral of x squared squared of 4 minus y squared dA. And your region R is bounded by this circle, x squared plus y squared equals 4. There is a hint. Notice that you have here, this is a circle. So I mean to say there are how many regions for a circle? If you're region 1, region 2, region 1, first quadrant, second quadrant is your region 2, third quadrant, region 3, and then fourth quadrant is region 4. So you have to consider these regions and take the double integral for its region. Okay, that's how you solve this problem. Region 1 is this from x ranges from 0 to the value uh, square root of 4 minus y squared x 0 4. Then ang y ranges from 0 to 0 to 2. This one, 0 to 2. On the second region, ganun pa rin. Y is from 0 to 2, pero ang x is from negative 4 square root of uh, negative square root of 4 minus y squared x up to 0. Underline, because this is supposed to be your x squared plus y squared is equal to kanina. Yan, x squared plus y squared is equal to 4. So your x there can be solved as the square root of, okay, 4 minus y squared. Let's have another example, 2.14. You are asked to find the double integral of y squared over x squared dA. Again, you should consider what should be either it's a dx dy or a dy dx. And you should consider what would be the limits of integration. So the region is bounded by the lines y is equal to x. Again, it's that line that slants upward to the right. Y is equal to 2, mean to say I have a constant value for y there, and hyperbola xy equal to 1. Hyperbola can be rewritten as either x equal to 1 over y or y is equal to 1 over x. So it looks like this. You can graph it. This is the region. This is your, this one, the red one is your xy equals 1. This is y equal to x, and this is your y equals 2. So y equals x, this one, black one, and the blue one is y equals 2. Now, if you take a look at this one, you can have the rectangular strip, you can have your d, this is supposed to be your dx, right? The ganun. And this is supposed to be your dy. So, kung pareho silang function ang limits of integration, then it would depend as to whether you're going to make use of the x or the y first. Whichever would be easier. You have to distinguish the two. In this case, we take a look. It's the function, right? So originally that one, but you can rewrite it as such. Notice that y, okay, your x is actually equal to 1 over y. From here, x, 1 over y. So x, this part, x is 1 over y, and it moves to x, this one equals y. This one, pag ganun. This is your x value, which is 1 over y, and it moves to the function value, x is equal to y. So you have 1 over y, and you should have your dx. On the other hand, for y, moving up there, your y moves from y equal to 1 to y equals 2. So it's a constant there. Okay. So this one, as soon as you're able to determine the limits of integration, then you can actually simply um, take its integral. In this case, the integral of x to negative y squared dx, so it's with respect, I mean to say, this one, you add 1, then over, so negative 1. over negative 1. So that's why it's negative x to negative 1. Then y squared is considered as constant. So 1 over y. And then evaluate, remember, is with respect to x. So you change this, okay, to y. So you should have y to the negative 1, negative y to negative 1. Then minus of minus, so that becomes plus. Y, this is 1 over y. This x becomes 1 over y. So that's y because it's negative 1 there. So y squared dy. Again, this can be simplified. This is simply negative y plus y cubed, but dy. So negative y, that should give us, okay, negative y dy, your y cubed. Simplifying further should give us y to the fourth, 1/4, minus, diba, square yan. So, y yan, so it becomes y squared 1/2. Evaluate 1. I think you can solve that one already. Simply have the upper limit. Substitute the upper limit. So that's 2 to the fourth. And this is 2 to the second power. Then minus that one, then minus 1/4, 1 to the fourth. And you have minus 1/2, 1 to the second power. So that should give us that value. And this is simply algebra, so you can solve for that one. That's equal to 9. Okay. So for double integrals in Cartesian coordinate, you have another activity that's 2.15. You only need to solve letter A. So solve only letter A. There is a hint for letter A. Notice that you have there, the problem there is to um, reverse the order of integration to evaluate the integral. So to be able to reverse the order of integration, because this one is a function, constant, you cannot simply rewrite it as dx dy and have the same limits of integration. You have to be able to consider this time your x here is from 0 to 4 and your y is from square root of x to 2. So when you reverse the order of integration, because it looks like this first now, your x is from 0 to 4. So x is from 0 to 4. 0 to 4 there, 0 to 4, and y is a function. That one. So what happens when you will have your uh, dy first, your dx first? So you have to consider those things. So references are as follows. Proctor and Murray will end with that one. And you can take a look at the video clips to also discuss. Stop sharing. Let me just go to this time and stop recording. Stop recording. Stop